In these two examples, we are looking to do some definite integrals, and they are going to have an inverse trig property that's going to be used in order to work through this. So first off, recognizing that we have this square root. This is not a perfect u substitution type of thing where you do the derivative of this inside and you have an x floating on the outside. So that option is gone, but it does have that feel to it. Now, the weird thing is that the 6 and the 54 are not perfect squares. So let's see what we can do to maybe make this formula look a little bit nicer. So here's what we got. First thing is we need to do some manipulation. And I'm going to do some u substitution, plug some things in, and we'll kind of play with that and see what we can do. So first thing I can do is I can actually factor a 6 out of these two. It doesn't feel like that's going to go anywhere for us, but it actually makes things really nice. So we have a 1/3 and a negative 1/3, and we'll have a 2 over radical 6, 1 minus 9x squared. That's a good thing. So surprisingly, it doesn't feel like we can do this, but we can take the 2 and the square root of 6 totally out of this problem. And then we'll have a 1/3. We'll have a negative 1/3. And so that becomes 1 over this piece. And I'm going to start setting it up towards having these perfect squares. So I know what I'm subbing in with this. So this is going to become 1 minus 3x squared. All right. So that means I have a u substitution because I don't perfectly have this x squared, so it's not as straightforward. So I want to do u to equal 3x, which means du is going to equal 3dx. I'm going to isolate the dx, pull the 3 over to make it a 1/3 du equals dx. All right, so one last substitution before we actually do our antiderivative is I now have a 1/3 multiplied to the 2 over root 6. And then at this point, you can change your bounds if you like. I don't really love the fact that those are 1/3. So if I back here, since I'm going into the substituting into u's, I can make everything into u's. So if I take this, multiply it by 3, I get a 1. And then multiply it by negative 1/3, and I get a negative 1. So my new bounds can look like that. So now everything is going to be in terms of u, and I'm looking at a square root of 1 minus u squared du, and that is a perfect substitution now. So that's just going to become inverse sine of u. And I'm going to leave everything in terms of u. So this is going to all mix together to make 2 over 3 root 6. This becomes the inverse sine of u. And I'm going to be plugging in -1 to +1. All right, so let's do the math. We have 2 over 3 root 6. And then inverse sine of 1 minus inverse sine of -1. All right, I just need to figure out what those values are. So inverse sine, you remember we have restrictions on it. Our answers are only going to come from first quadrant and fourth quadrant. So like a negative 90 to a positive 90, or negative pi over 2 to positive pi over 2. And sine of 1 is at pi over 2. So 2 over 3 root 6 of pi over 2 minus, and then our sine of -1 occurs here at negative pi over 2. So let's clean this up. 3 root 6. You got a pi over 2 minus a negative pi, which is plus a pi over 2. So pi over 2 plus pi over 2 is pi. And so then that mixes together to give us a 2 pi over 3 square root 6. Now, that's fine, but they may ask you to rationalize the denominator. So let's just do one last couple steps. We'll multiply by square root of 6. And so you're looking at um, this is going to be 6 times a 3 is 18. So a 2 pi root 6 over 18, which can simplify, make that a 1 and a 9. So you're looking at pi square root 6 over 9 as your area under that curve. All right, so let's do one more. So this one, again, kind of rough looking. We're probably going to have some u substitution because that's not a perfect square. I mean, it is, but we're going to have to rewrite it. So we're going to have a u substitution. I could pull the 4 off of this. This has an inverse tangent field to it. So let's rewrite that to make that work for us. And so I'll pull the 4 off. I have a 1 over root 3 and a 1/3. 1 over. Let's start to get this ready for our u substitution. Plus 1 squared dx. All right, so I'm going to let my u equal 3x. I'm going to let du be 3dx. 1/3 du equals dx. So we have a 1/3 multiplied by the 4. I'm going to change my bounds, and we're going to have a 1 over u squared plus 1 du. So it perfectly has what the formula wants it to be. Okay, we perfectly have this. So it's just going to be 1 tangent or inverse tangent of u, right? Because my a's are 1. So changing my bounds is me multiplying this by 3. So it's going to be 3 over root 3, which we'll clean that up. Multiply by root 3, multiply by root 3. So that's 3 root 3 over 3. Cancel out your 3's. So your upper bound is just root 3. And then if I plug in 1/3 into this, I get a 1. All right, and so this is still smaller than this, so I want to make sure that I'm still in the right order. So that's still smaller. And then let's do the formula. This is just an inverse tangent. This becomes 4/3. This is inverse tangent of u from 1 to root 3. All right, so let's plug some stuff in. 4/3. We have inverse tangent of root 3 minus inverse tangent of 1. So 4/3. So inverse tangent of root 3. So I go to a 30, 60, 90. This is where my root 3 triangle is going to come from. 30, 60, 90. And then I know I have a 1, 2, root 3 relationship with those sides. And so tangent of 60 is going to get me opposite over adjacent. So pi over 3 on this one. And then inverse tangent of 1 comes from the 45, 45, 90. Because you have that relationship with your sides. And tangent of 45 is 1 over 1. So then we're subtracting pi over 4. All right. So now on to, let's just figure out how to put the fractions together. So if we put our fractions together, we're looking at 4/3. This is going to multiply by 4 to match that denominator. So 4 pi over 12 multiplied by 3, 3 pi over 12. So 4/3 times 4 twelfths minus 3 twelfths is 1/12. So pi over 12. Mix that together. 4 can simplify. 1 and a 3. And we're going to get an answer of pi over 9. All right. That was finding a definite integral involving inverse trig function.